So this is the last session before we lunch. And we started kind of staying on topic with Daniel Gratzer talking about the Yoneda embedding in simplicial type theory.
Right. So first things first, all of this is joint work with Jonathan and Ulrich. Is this function? No? All right, cool. Actually, Felix, I might need a hand here. Will this work? All right, cool. All right, that works. So anyways, what are we trying to do? So the starting point to all of this is that dependent type theory and sort of category theory are interesting, and I'd like to make them more interesting by combining them. I have no intention of justifying why these things are interesting because we just had a talk on it, and most of you are now at a workshop on type theory, so I assume there's some buy-in on that point. Yeah? So specifically, I want to talk about a variant of homotopy type theory, which is sort of tuned for proving facts about infinity one categories. So the goal here is to formulate a type theory that lets us prove facts about ordinary infinity one categories as mathematicians use them. All right? Now, the thing that makes this challenging, which Bastian was alluding to several times, is just that type theory is designed to work with objects that fundamentally behave like sets. They don't have to literally be sets. You can work with, sheaves or groupoids or infinity groupoids. But categories sort of fundamentally break from these objects because they have direction, they have variance. And sort of a more technical way of saying this is that the category of categories, no matter how you slice it, infinity or not, is just not locally Cartesian closed. And this means that it just doesn't support things like dependent products that we're used to having inside models of type theory. Okay. And of course, there's other complications. There are just operations on categories that don't have obvious counterparts if you're thinking about groupoids or sets. This is things like the opposite category. And there are kind of two clear approaches that we can take for designing such a type theory. So option number one is we change type theory a lot. We start discarding the ability to have arbitrary dependent products, and we start adding these new operations for opposites and things like that. And this is what we could broadly call directed type theory. But there is an alternative approach, which is to change type theory only a little bit, maybe add some modalities and some axioms to sort of capture some new operations, but then work with a much larger category that fully faithfully embeds all categories. So we sort of weaken the idea that every type is a category to just some of the types are categories. And we're going to focus on the second approach. A lot of people have worked on the first approach, and that was sort of what we just had a talk on. So there's plenty of related work if you prefer the first. All right. So we're going to follow the approach laid out by Emily Reel and Mike Schulman. We're going to switch from considering interpreting type theory into something like cat to embedding cat into simplicial spaces. So this is a much larger category that contains all categories, but happens to be an infinity topos. And because it's an infinity topos, it admits a model of hot. And so we can start to add axioms that are validated by this model to try and tune homotopy type theory to sort of better fit this one particular model. And in order to do so, we want to have a bunch of modalities. These are like non-fibered connectives that don't respect substitution and behave a little bit weirdly. I don't really want to talk about these. There's a big pile of inference rules that you add to type theory that makes all of this work, and it's kind of what I wrote my thesis on. But for the sake of trying to focus on the actual application, let's just put all of that in the background. All right. All right. So more concretely, we extend hot with 4 modalities, a la multimodal dependent type theory. And the most important of those are the opposite modality, which I write with this O, and a groupoid core modality, which I write with the flat. And we have 8 axioms that we add in addition to these. And the most interesting axiom basically says, there exists a type I, which is a bounded distributive lattice. And the idea is we're going to visualize this type I as something like the directed interval. So the top and bottom of this bounded distributive lattice, that's our 0 and our 1. And the meets and joins are going to allow us to define an inequality relation, which gives this thing a direction. And so if we visualize I as this 0 to 1 line, we can use the ordinary constructors of dependent type theory to sort of isolate different shapes. So taking I times I, we now have a cube. Using the inequality, we can carve out the subtype of the triangle, which I've illustrated here and I've called delta 2. And if we further restrict that using the operations of type theory, we can get the horn, which is these two composable arrows here, written with a lambda 2, 1. And using pushouts, we can glue together copies of delta 2, 1, or delta 1 and delta 2 again, to get the walking isomorphism, which is a single arrow with a section and a retraction. Okay? So these are all things that we can just start to isolate using the theory of dependent type theory. And we can also likewise define what a synthetic morphism is in an arbitrary category. So this is just going to be a function from the interval to that type. And if we want to talk about morphisms from C to D, let's say, like a CD colon big C, then we just add boundary conditions, saying that when you evaluate this function from I to C at 0, you get one thing, and when you evaluate it at 1, you get the other. So far, so good? All right. So we're working in a larger category here, which means that not every type behaves like a category. And so in particular, even though I can talk about synthetic morphisms in an arbitrary type, they don't really behave like morphisms that you expect. You always get the identity, but what you definitely don't get in all situations is the ability to form composites. So what we need to do is add a property on types. So this is a map that takes something in the universe and gives you back an H-prop. And this is basically going to say, this type, whatever it is, has composition. And this is not structure. This is not like something that you have creativity in defining. It's just the proposition that whenever you have a composable horn, so this is this C to the lambda 2, 1, there is a unique way to extend it to a commuting triangle. So every composite has a unique extension to a commuting triangle. And because we're talking about the theory of infinity 1 categories, we also want to impose this local univalence condition. So the way to think about this is we're working inside of HOT, which means every type has an intrinsic notion of equality attached to it. There's just the identity type floating around, right? And if we're working in a category, like one of these types that has this composition operation, we can also start to talk about another intrinsic notion of equality, namely isomorphism. So we have a certain redundancy, right? We have things that are like very equal because the identity type says they're the same. And then we have the things that are like mostly kind of equal because there's an isomorphism between them, a synthetic isomorphism. And the second is-equiv says that these two things collapse. So this is the rest condition, which says that synthetic isomorphisms are exactly the same thing as just a normal identity type in HOT. All right. And it's worth noting that in addition to categories, we can isolate groupoids, as Bastian was talking about, just by talking about the types which believe that the interval is contractible. So these are the things that are completely agnostic to this category structure. They just behave like groupoids. And I was worried that that was too much math, so I drew a picture. So you can kind of think of all of this as like having 3 different zones, yeah? So the innermost zone, the most special types, these are the groupoids. And this is basically just the stuff that we have from ordinary homotopy type theory. So it's like bool and nat. And I mentioned we had this like this modality for groupoid core, this flat. That's always a groupoid as well, which makes sense given the name. And then like there's the cool stuff in this theory, the stuff that we actually want to work with and prove things about. And those are the things that are actually categories. So the synthetic interval is a category, delta n is a category. We're going to meet one on the next slide called S. And then in order to make this like an actual dependent type theory with all the normal connectives, we have the stuff which is not a category or a groupoid, but just an arbitrary simplicial space. And the most important one that you run into all the time is the universe. The universe is just way too unstructured to form anything like a category. There's no constraints on how you map the interval into it. It's also the case that sometimes you can take some categories and sigma them up and you don't get a category. But for the most part, we care about the inner 2 rings. And the outer ring is just there to let us write down statements in type theory about it. Okay? All right. So the focus of this particular work and the thing that I wanted to focus on in this talk was combining 2 things that had been done previously. Yeah. So Riel and Schulman and César had built up the theory of limits, colimits, adjunctions in ordinary simplicial type theory. And my collaborators and I recently constructed a type inside of simplicial type theory, which is the directed univalent category of groupoids. So this is a subtype of the universe, which is a category, unlike the universe, whose objects are spanned by groupoids and whose morphisms, synthetic morphisms, correspond to just functions. And with these two things to hand, we can actually start to develop the basic theory of category theory. So we can get the Yoneda embedding, we can derive that free sheaves are co-complete and complete and have the expected universal property as a free co-completion. And we can, formulate and prove the existence of Kahn extensions and prove Quillen's theorem A and a bunch of other stuff. I'm going to be honest, this talk in this paper doesn't really stop where we ran out of things to say. It stops where we ran out of space in our lick submission. So this is sort of like enforced by the page limit in that way. All right. So the big idea for most of these results is sort of like a three-step approach to solving all of these problems. So you want to show that something holds for all categories. So step one is you show that it holds for S, the category of groupoids. And this is usually easy because of directed univalence. You can usually reduce the statement to just something in ordinary hot by translating synthetic morphisms to just ordinary morphisms or ordinary functions. And then you argue that whatever this property was, you can check it pointwise in a functor category, which means you can now get this result in all free sheaf categories. Okay. And then you make this argument that every category embeds into a free sheaf category by the Yoneda embedding, and you somehow claw back this result from holding from free sheaves on C to just C by using this embedding. And it's this last step which is the kind of crucial bit here. It's the ability to realize C as a full subcategory of free sheaf C. That's the main technical construction. And it's this definition of this phi, which is the Yoneda embedding, which goes from the opposite of C times C to the category of groupoids S. Okay. So since this is the main technical contribution, I feel obligated to say a few words about how it's actually done, but I don't honestly want to say that many. The most important bit is that we realize the total space of this phi primitively in the theory. So this is the twisted arrow category, whose objects correspond to morphisms in some type. Let's say we're talking about C here. So the objects of the twisted arrow category on C are going to be arrows in C, and the synthetic morphisms in this category correspond to not squares, but twisted squares. So if you look at the diagram that I've drawn here, notice that the top arrow points towards me, and the bottom arrow points towards me, and the top arrow points away. So in particular, they point in opposite directions. And if you think about this sort of geometrically, you can project out the top and project out the bottom, and you'll get something that lands in C op and C. And so this we realize as a modality. We have an axiom that it represents the right functor. And this is basically how we get a hold of phi. And then you can make an argument that taking fibers lands in S. This is a somewhat technical condition, but we can prove it. And then with all of this to hand, you actually have something that behaves like a fully functorial version of Hom, which has the correct variance in both arguments. Okay, at the end. So with this to hand, we can start to actually prove some stuff. And the main thing is that we can start to prove various sort of rectification results. This is sort of what Bastien was talking about, where you prove something about objects. So you want to show that some property sideways, and you show that it holds non-functorially. You don't explain how to extend your choice of witnesses functorially, but you just show that it holds for everything in the groupoid core. And then you uniformly extend it to a fully functorial choice. And so the two most important instances, both of which crucially rely on having the Yoneda embedding around, are if you have a natural transformation between two functors, and non-functorially, each leg of this has an inverse, then that choice of inverse is actually automatically functorial and assembles into a natural inverse to this natural transformation. So pointwise natural transformations that are invertible are just invertible. All right. The other instance is a little bit more technical, but basically says if you want to show that something is a left adjoint, it suffices to construct the right adjoint kind of locally, object-wise, and to show that there exists a representation of this particular functor for each object, but the representation doesn't need to be chosen functorially, it's automatically functorial. Okay. And with this last one to hand, we can actually start to construct some concrete examples of adjoint functors. So we have the fact that precomposing between pre-sheaf categories is both a left and a right adjoint. We have that the inclusion of truncated spaces into spaces forms a right adjoint, and so on and so on. And I want to emphasize, in all of these instances, it's somewhat obvious what the appropriate adjoint is supposed to be. Like, we knew what it was going to be going. It was not surprising that the adjoint existed. The issue is that it's hard to write down inside of this theory what the adjoint is supposed to be naively, because it involves some non-trivial construction which is not obviously functorial. Like, the truncation modality is going to give rise to the adjoint to the second point. But it's not obvious that that higher inductive type assembles into some sort of functorial thing that actually descends to a map S to S. So that's the whole purpose of having this additional machinery of checking things object-wise, to avoid all of that complexity. Oh no, is this not advancing now? There we go. All right. And from these examples, we can get quite a few recognizable statements. So from the last example of an adjunction, we can get the universal property of pre-sheaf categories. And from that, combined with the first example, we can get that Conn extensions exist when you expect them to exist, when there's enough colimits around. Okay. Absolutely no details on that. All right. So the last little bit that I wanted to talk about was Quillen's theorem, which we can derive from having Conn extensions around. So this is quite a useful theorem that gets kind of applied all over the place in infinity category theory. It allows us to reduce computing some colimit over a complicated diagram to a suitably simpler subdiagram, provided that that subdiagram satisfies a technical condition, which is the second point in this list. All right. And for an example of how this can be applied, we're actually able to prove now that co-Cartesian maps are proper. So this is another rather useful theorem that gets used in various technical places. And what this says is that if we have some map between types and it's co-Cartesian, not too many details on what that is, and we have that A to B is final, then we're able to pull that back and obtain something which is also final. And this is not generally the case. In particular, this doesn't hold in Cartesian. This doesn't hold for Cartesian fibrations, for instance. And I felt obligated to give a few examples of what it looks like to actually work in this theory. So the idea of how you prove this is we're going to apply theorem A, so that we need to prove that this type up here is equivalent to the unit type. Yeah. And circle groupoid is the reflection from arbitrary types into groupoids. So this inverts all the synthetic morphisms and just gives you a groupoid. All right. And the thing that I mostly wanted to emphasize is that the actual calculation that this thing is contractible is very type theoretic and not particularly higher categorical in spirit. Like, it mostly just boils down to shuffling around sigmas and equalities. So the first line is sort of shuffling around what it means to be an element of the slice category E co-sliced over E, using the fact that pi is co-Cartesian. This is just applying a property, then rearranging stuff using ordinary type theory machinery. We end up in this situation where we have, something complicated looking, but in particular, we have contractible fibers in this sigma type, if we could only nullify them. But because we have a reflective subuniverse of groupoids, we have all the machinery of RSS available to us. So we can shift from having the groupoid modality on just the outside to apply to each fiber as well. And that causes each fiber to disappear. And then we can apply theorem A again, and then we're done. And so in particular, even though the result is quite non-trivial, the argument is basically completely formal and mostly type theoretic. I think that was all I really wanted to say. If you want actual details, the preprint for this is on my website. And if you want details on how we constructed S, that's on archive. All right, thank you.
Okay, questions?
I have two questions, I think. So first of all, this twisted thingy, the twisted arrow construction at the beginning. So this is something that you added to simplicial type theory?
Yes.
Something new?
Yes. So I mentioned very briefly that there were 4 modalities in the system. So those four modalities are opposite, core, the right adjoint to core, sharp, and this T, this twisted arrow modality. So this is a primitive input to the theory that we're putting in there. Of course, it's not ideal to be in the business of bolting on new things to the theory every time we want to do a new construction, but the Yoneda embedding is sufficiently primitive that we think it carries its weight.
Okay, so there's no way to construct this out of the simplicial layer or something? Or another?
I wouldn't say that. I would say that I'm not sure how to do it yet.
Okay. All right, so
yeah.
Can you also kind of hint on how the twisted modality kind of interplays with the other modalities? Are there some axioms?
Yeah, so they're not axioms per se. The way that we set up this modal type theory is using MTT, which is parameterized by a two category. So the two category controls all the interactions between the twisted arrow modality and like the opposite modality, core, sharp, etc. And we have various axioms saying, for example, that if you take the twisted arrow of the opposite category, this is the same as the twisted arrow of just the normal category, though that equivalence is non-trivial. And then there's also the two projections from the twisted arrow to just C and C op. Those are also controlled by the mode theory. So that's where that's introduced.
Okay, nice. Okay.
Mm-hmm.
There was a phi on some of your slides.
I think there's a phi on this slide.
No, upside. Okay.
Oh,
sorry.
yes.
Yeah, this one. What was this one?
I just needed a stand-in letter for various properties.
Oh, sorry.
Yeah. So the two bullet points on the bottom are the things that these are.
More questions?
It's one in Zoom. Lucy, do you want to try and unmute?
Yeah, can you hear me?
Yes.
Perfect. I would like to know if you could say a few more words about why you chose those why you chose to add those modalities, and whether that is a set of things that, or a collection of things that could be reduced or changed, or I'd just like to know a little more about that choice.
Sure. So each of the modalities we added does something rather important. So I don't think that we can just discard any of them. To be concrete, the opposite category is sort of self-explanatory. We just use that to state theorems that involve the opposite category. We use core all over the place to state object-wise properties. And we use sharp, which is the adjoint to the core modality, to define, for instance, full subcategories or wide subcategories. So each of those sort of has a role to play. As to how we arrived at them, more or less, we wanted to state theorems that involved them. And so they got added to the theory. So this is very much a sort of like experimentally arrived at set of axioms.
Solid. All right, thanks.
Mm-hmm.
Maybe a short question.
So in the definition of ISCART, you said that like one-dimensional forms can be filled, or two-dimensional forms can be filled, essentially. You don't need this for higher dimensional ones, right?
No, it follows automatically because this equivalence is stated within type theory and in particular relative to a context. So if you can fill two horns in a context that has a bunch of simplices floating around in it, then you're secretly filling a higher dimensional horn.
Thanks.
Okay, then let's thank Daniel again.